Hello, welcome back. In the last class, we have derived the relationship between the angular frequency omega and the wave vector k of elastic vibrations in crystals with a monoatomic basis or monoatomic molecule. Now, today we will be doing the derivation of the relationship of omega and k in diatomic molecule. Okay. So before going to that, let us see in the monoatomic case what is the group velocity. Okay. Group velocity means we are talking about the elastic vibration. So the speed of energy propagation is called group velocity. So group velocity of a wave is given by Vg, okay, is equal to d omega divided by dk. Okay, or we can say that this is the gradient of omega with respect to k. Okay, okay, gradient of omega in k space. We know that omega square in this case is 2c by m into 1 minus cos k. Okay, so this relation we have derived in the last class. So from this we can say that this is equal to 2c by m. 1 minus cos k is equal to 2 sine square k by 2. Okay. So from this we get omega is equal to root of 4c by m sine ka by 2. So this is the modulus of sine ka because omega is always positive. Now we know this expression for the group velocity, which is the velocity of vibrations or velocity of sound in the crystal, okay, is equal to the gradient of this thing with respect to k. So we have to differentiate with respect to k. So this is equal to root of 4c by m into cos k by 2 into a by 2. So this can be written as, so this 4 and this root of 4 and this 2 get cancelled, this a goes inside. So this can, we can write this thing as c root of c a square by m cos k by 2. Okay. So this is the general expression for the group velocity in the case of vibrations in monoatomic crystals. Okay. Now let us see the long wavelength limit case. Long wavelength means in the long wavelength limit, this lambda is large. That means k, which is equal to 2 pi divided by lambda. When lambda is large, k is small. So in this limit, we can write ka is very much less than 1. So in this case, the equation for omega square we have seen in the last class, that is omega square is equal to 2c by m 1 minus cos k. Cos k can be written as, so this is cos x. Cos x is equal to 1 minus x square by 2 factorial plus x raised to 4 by 4 factorial, etc. So in this case, cos k is k square a square by 2 factorial is 2. When k is very small, then we can neglect the higher order terms. Okay. So we'll get these things. Now if we substitute in this, we'll get omega square is equal to 2c by m 1 minus cos k. So 1 minus k square a square by 2. So this is equal to um, k square a square by 2. So which is written as c by m k square or omega. So we can say that omega is equal to root of c by m k a. Okay, so a is the lattice parameter and m is the mass of the atom in the basis and c is the force constant, okay, of the atom. Now here this omega is directly proportional to k, okay. Therefore the group velocity is root of c by m a. So it is independent of the wave vector k. Okay, the group velocity which is d omega by dk is independent of the. So we can draw the graph of group velocity versus k. So we know that this group velocity will be constant in the log. Okay, so it is constant c by ma. So this value is c by ma, and as k increases, so we will have to see this is the equation for this is cos ka by 2. Cos theta will become 0 at pi by 2. So at pi by a, when k is at pi by a, this become 0. So this is the graph of group velocity. We have plotted the omega versus k graph in the last class. So if you take the slope of this curve, then also you will get the group velocity curve. Okay, that is about the group velocity in the monoatomic case. The diatomic case we will see in the next lecture. Okay.